Welcome to the Deep Dive, the show where we cut through the noise and get right to the core of what's fascinating and, well, important in tech and beyond. It feels like just yesterday we were all trying to wrap our heads around what a chatbot even was, just marveling at AI that could generate text or, conjure images out of thin air. But the AI landscape, it's shifting at light speed. Seriously. We're moving beyond AI that just generates content. Now we're talking about AI that acts, that collaborates, that effectively takes on entire projects.
It's true. The pace is just staggering. Just when you think you've sort of caught up, a new paradigm emerges. It completely redefines what's possible. And maybe more importantly, it changes our relationship with these intelligent systems.
That's precisely what we're digging into today. Our mission is to demystify this fascinating world of agentic AI, what it is, how it fundamentally differs from the generative AI you might already know, and then we're going to explore a powerful framework called LangGraph. That's one of the things making these advanced systems, well, a reality. Our goal is to equip you with a solid understanding, explain the what and the why, and hopefully leave you feeling truly well-informed about this next frontier of AI.
Yeah, and to do that, we've gone deep into the source material. We've pulled together insights from, cutting-edge research papers, detailed technical docs, practical guides, really trying to get a comprehensive look at how these technologies are being built and, what changes they might bring.
Okay, let's unpack this then. To truly grasp agentic AI, we first need to set the stage. We need to understand what came before it, or maybe what's often used with it. Let's kick things off with generative AI, or Gen AI. Many of you are already interacting with this daily, right?
That's a great starting point. Generative AI, at its core, is fundamentally, well, reactive. It's a powerhouse, no doubt, but it's reactive. Imagine it like an incredibly intelligent but very patient assistant. It's always waiting for your prompt, your instruction. Its main purpose is to generate content, text, images, code, audio based on patterns it learned from vast data sets, and crucially, the specific input you give it.
So it's like a highly sophisticated pattern matching machine, isn't it? It's analyzed huge amounts of data, learned the statistical lengths between words or pixels, and when you prompt it, it's basically predicting what comes next based on those patterns, like it's an expert at finishing your thought.
That's a very accurate way to think about it. And here's the key distinction for Gen AI. Its work typically ends at generation. Once it spits out the text, the image, whatever, it stops. It doesn't take further steps unless you, the human, give it explicit new instructions. Another prompt. The human role is very active here. You're constantly reviewing, checking, refining, directing. The AI generates possibilities. You curate them.
Right. So examples that we all know would be chatbots like ChatGPT or Gemini image generators like Dedali, maybe even those tools that write code snippets.
Yeah.
They produce the output, and then they just wait for your next move.
Exactly. Imagine asking a super smart writer to draft a story. They write it beautifully, hand it over, and then they stop. They're waiting for your feedback, your next instruction, maybe a completely new request. That's the reactive nature of Gen AI. It's incredibly powerful within its scope, but it's initiative. It's tied directly to your input, always on demand.
Okay. Now let's shift gears. Let's introduce agentic AI. This is where the narrative completely changes, right? If Gen AI is reactive, agentic AI systems are decidedly proactive. They don't just wait for the next command after producing something. They take initiative.
That's the fundamental difference, yes. Their core purpose is to pursue goals through a series of actions. Often it starts with a user prompt defining that ultimate goal, sure, but then they embark on this iterative life cycle to achieve it, often with minimal human intervention. This life cycle is a continuous loop. First, the agent perceives its environment, gathers information, scans emails, checks stock prices, whatever it needs. Then, based on that perception and its goal, it decides the next action. After that, it executes the action, often using external tools or APIs, sending an email, making a booking, running code. And finally, it learns from the output. It observes the result, adjusts its understanding or plan. This loop just keeps going until the goal is met, or it hits a snag where it really needs human input.
So it's not just a one-off output. It's more like an ongoing management system for multi-step processes. That dramatically changes the human role, doesn't it? Instead of constantly directing, we're stepping in only when absolutely necessary, like a manager delegating a project.
Precisely. The human input is sought only when needed, maybe for clarification on a tricky decision or approval before a big step. Think of examples like a personal shopping agent. It doesn't just suggest products, it actively monitors prices, places an order when a deal pops up, handles checkout, coordinates delivery, or an AI assistant planning a complex event like a big conference from start to finish independently.
That's a great analogy. So if Gen AI is asking a smart person to write a story and they hand it over, Agentic AI is asking that same smart personal assistant to organize an entire conference. They'll independently research venues, check availability, send invites, coordinate catering, and only bug you for key decisions or if there's a real problem. That's real initiative, a shift from tool to collaborator.
Indeed. And what's fascinating is that despite these big differences, both Gen AI, especially chatbots, and these agentic AI systems often share a common foundation: large language models, LLMs.
Right. For generative AI, LLMs are the backbone for generating text, obviously. But how do LLMs power agentic AI differently? It sounds more profound.
In agentic AI, LLMs provide the crucial reasoning engine. They're not just generating text, they're generating essentially thought processes and making decisions based on them. This brings us to a key concept: chain of thought reasoning. It's how LLMs enable agents to think and tackle complex tasks. The agent breaks down a big goal into smaller, logical, sequential steps. Much like humans do, right? It's like the LLM is having an internal monologue.
So it's not just generating the answer, it's generating the steps to get there,
Yeah.
or maybe the questions it needs to ask itself to figure out the steps.
Exactly. The LLM generates this internal thought process to explore the problem space before committing to an action. For instance, that conference planning agent. Its internal thought might be something like, okay, first, I need all the requirements: attendee count, budget, tech needs. Then, research venues matching those. After that, check availability, compare prices. This internal dialogue, powered by the LLM, drives its decision-making and allows for that complex, multi-step planning.
That makes total sense. And looking ahead, it seems the most powerful AI systems won't be strictly one or the other, but a blend, like intelligent collaborators.
That's definitely the vision. These future systems will intelligently understand when to explore options through generation, brainstorming ideas, drafting copy, sketching designs. And crucially, they'll also know when to commit to courses of action through agentic behavior, executing a marketing plan, interacting with booking APIs, proactively managing your schedule.
So an agent that knows when to, say, generate the next chapter of your fan fiction, it's generative, and when to proactively manage your calendar, find resources for a project, or even automatically A/B test marketing and adjust ad spend based on real-time data, that's agentic. That's a powerful combination.
Right.
Moving from just producing stuff to actively managing and optimizing strategic tasks.
Exactly. It creates a highly versatile, intelligent assistant, capable of both creative output and practical execution. It brings a whole new level of autonomy to our digital world.
Okay, so we've drawn the line between generative and agentic. But there's a finer distinction within the agentic world that's important: the difference between a single AI agent and a broader agentic AI system. Let's start with the basic building block. AI agents, what exactly are they?
Right. An AI agent is basically an autonomous piece of software designed for goal-directed task execution within a specific digital context. It functions with minimal human input after you set it up. It perceives inputs, reasons, executes actions in real time. But the key thing is, they're typically task-specific, optimized for narrow, well-defined jobs like, say, filtering your email, searching internal company docs, or simple database queries. They react to inputs from users, APIs, other software.
So like a specialized bot, an AI agent that finds news, summarizes it, sends it back a single defined workflow. It's not like something many of us might already use, sort of digital specialist.
Exactly. It's a specialist. Now, agentic AI takes this a significant step further. This is where you bring multiple AI agents together into a team to achieve much more complex goals. The analogy shifts from a single specialist to an entire coordinated project team.
A team. That's interesting. So what are the key features of this team-oriented agentic AI? What makes it more than just several individual agents running side by side?
Well, when you have multiple agents working together, you gain several powerful capabilities. First, task decomposition. The big, complex goal gets automatically broken down into smaller, manageable subtasks, each often assigned to a specialized agent. Then there's inter-agent communication. These specialized agents need to share updates, results, often through sophisticated messaging or shared memory. Crucially, they also have memory and reflection. Agents remember past steps, learn from outcomes across interactions, refining their approach as a group. And finally, there's orchestration. You need a lead agent or a coordinating system to ensure the whole team works together cohesively, manages dependencies, resolves conflicts.
Okay, so for our vacation planning example, one agent books flights, another finds hotels, a third checks visa stuff, a fourth finds local activities, and a coordinator makes sure preferences are met, the itinerary lines up, everything clicks together. That sounds like a true collaborative effort, like a human travel agent with a team.
It is. Or think about a smart home. A standalone AI agent might be your smart thermostat, just focused on temperature. But agentic AI would be the system managing overall energy use for the whole house, coordinating the thermostat, smart lights, appliances, maybe factoring in weather forecasts, your schedule, all based on real-time data and your preferences. It's a holistic, coordinated approach, systems interacting intelligently for a broader goal.
That smart home analogy really clicks.
Right.
So let's talk architecture. How does the blueprint of a single AI agent differ from an agentic AI system? What fundamentally changes in the build?
The differences are quite profound, yeah. Moving from an individual focus to a collective one. In terms of design, an AI agent is typically one agent, one task, often working alone. Agentic AI involves multiple agents, distinct roles, a team structure. For communication, a single AI agent usually doesn't need to coordinate much. Agentic AI, however, relies on constant structured communication among agents, sharing context, progress.
And memory. That seems crucial for complex, evolving tasks.
Absolutely vital. A basic AI agent might be stateless or have minimal history, just remembering the immediate context. Agentic AI, though, boasts persistent memory, remembering past tasks, outcomes, strategies, what worked, what didn't. This is essential for long-term planning, learning, adapting over time. Regarding reasoning, a single AI agent often follows linear logic, do A, then B, reacting directly. Agentic AI uses iterative planning and replanning, leveraging advanced reasoning frameworks to adapt, anticipate, recover from issues. This also impacts scalability. An AI agent is limited by its task scope. Agentic AI can scale to handle much more complex, multi-agent, multi-stage problems.
And this translates directly into their typical applications, right?
Right.
So like very different levels of ambition here.
Yes, exactly. AI agents, you find them in customer service chatbots, internal search tools, simple workflow helpers like email sorting. Standard stuff, really useful. Agentic AI, it's built for more sophisticated things. Multi-agent research assistants synthesizing complex reports, robotic coordination in manufacturing or logistics, collaborative medical decision systems pooling AI expertise, adaptive workflow automation managing entire business processes end-to-end, learning and optimizing on the fly.
So what architectural enhancements actually allow this jump? From a single agent to a full agentic AI system capable of all that? Sounds like more than just adding more agents.
It's definitely more. It's about building layers of intelligence and connectivity for that team dynamic. First, the move from single to multiple agents means designing specialized agents that interact via robust channels, message queues, shared memory, maybe a central blackboard. Second, agentic AI integrates advanced reasoning capabilities. We're talking frameworks like React reasoning and acting, where the agent explicitly thinks, then acts. There's chain of thought, like we discussed, and even more complex structures like tree of thoughts, letting agents explore multiple reasoning paths, self-correct, basically brainstorming internally before acting. These allow agents to break down tasks, evaluate intermediate results, and dynamically replan.
And memory, I assume, is foundational here, allowing them to really learn and adapt over time, not just in one go.
Oh, absolutely critical. For long horizon planning, sustained intelligence. Agentic AI incorporates sophisticated persistent memory systems. These include episodic memory, like a detailed log of what happened during a specific task, semantic memory storing long-term facts, general knowledge, and crucially, vector-based memory, which is fundamental for retrieval augmented generation, RAG. This lets agents pull relevant info from vast external knowledge bases, grounding their decisions in facts, fighting hallucination.
This sounds incredibly powerful, almost like a step towards, well, more general intelligence. Where are we actually seeing these in the real world now? What impact are they having?
Well, AI agents are already streamlining customer support, enabling better internal search, filtering info. They're pretty common. Agentic AI, being newer and more complex, is enabling things like multi-agent research assistants that can sift through scientific literature, synthesize findings, maybe even suggest hypotheses, accelerating discovery. We're seeing it in robotic coordination, like managing drone swarms for infrastructure inspection or farming. In healthcare, collaborative systems are starting to pool AI expertise to help doctors diagnose rare conditions or personalize treatments. And in business, adaptive workflow automation. Think dynamically rerouting supply chains in real time based on disruptions, optimizing without constant human checks.
But with great power
Yeah.
comes great complexity, right?
Yeah.
What are the current limitations and challenges? Sounds like a lot of moving parts.
Indeed, the complexity grows exponentially. For single AI agents, limitations often come from the underlying LLMs. Lack of true causal understanding, hallucinations if not grounded well, sensitivity to prompts. They also struggle with long-term planning and graceful failure recovery. With agentic AI, these problems get amplified, and you can have inter-agent error cascades, one agent's mistake messing up the whole team, coordination breakdowns. There's also emergent instability, complex interactions leading to unpredictable behavior, scalability limits as you add more agents, and explainability becomes really hard. Tracing why a team of agents decided something is incredibly difficult.
So how are developers tackling these challenges? What emerging solutions are making these systems more robust, more reliable?
Several key solutions are helping. Retrieval augmented generation, RAG, is vital. For single agents, it cuts down hallucinations, expands knowledge. For agentic AI, it acts as a shared grounding mechanism, keeping all agents on the same factual page. Then there's tool augmented reasoning, often via function calling. This lets LLMs use external tools. Super important for both. Single agents can interact with the real-world booking API's databases. Agentic AI needs it for autonomy, structured coordination among agents using specialized tools, and finally, robust memory architectures are constantly being improved, addressing those long-horizon planning issues, letting agents truly remember and learn from the past.
And the future vision. Where are AI agents and agentic AI heading in the next few years?
We can expect AI agents to become more proactive, learning over time, handling more complex logic. For agentic AI, the future involves teams managing intricate real-world workflows, optimizing manufacturing, managing financial portfolios dynamically. We'll also see better simulations for testing multi-agent plans safely before real-world deployment, and crucially, a big focus on governance systems for ethical coordination and control. It's a future where AI is even more integrated, more intelligent, taking on tasks needing deep understanding and proactive problem solving.
Okay, so we've laid the groundwork. Reactive generative versus proactive agentic. Single AI agents versus multi-agent agentic AI systems. We see the potential. Now, let's get practical. How do developers actually build these sophisticated systems? Things like RAG and tool-augmented reasoning are great, but implementing them for complex teams isn't trivial. You need a solid architecture. And that's where specialized frameworks come in, right? Streamlining development. This brings us to two key players, LangChain and LangGraph. Let's start with LangChain.
Right. LangChain is probably the most widely known framework for building LLM apps. Its core idea is providing an abstraction layer, letting you build applications by executing sequences of functions in a chain. It's like a general-purpose toolkit for a huge range of LLM applications.
Can you give us a classic LangChain workflow example? Like if I want to grab some info, summarize it, then ask a question about that summary. Seems super common.
Absolutely. That's a classic retrieve, summarize, answer workflow, often called RAG. With LangChain, you'd stitch together components in sequence, a component to fetch data, maybe from a PDF, another to split it into smaller chunks, then a summarization component, basically a prompt plus an LLM to create a summary. And finally, an answering component, maybe with memory for conversation history, another prompt, another LLM to generate the answer based on the summary and context. It's like an assembly line for AI tasks.
So its modularity is a huge plus. You can swap out LLMs, data sources, just piece to the components like building blocks.
Exactly. Its architecture really promotes modularity. Huge ecosystem, integrations for tons of models, tools, data sources, pre-built components like prompts, memory buffers, tools like search or calculators. But regarding state management, LangChain generally keeps a more limited forward-passing state. It does have memory components for conversation history within one interaction, but it's not designed for a core, global, shared memory across an entire dynamic workflow in the same way LangGraph handles it. It's fundamentally built for linear execution.
Which brings us perfectly to LangGraph, the star of today's deep dive. How does LangGraph build on or differ from LangChain, especially for those really dynamic multi-agent systems we talked about?
LangGraph is a specialized library within the LangChain ecosystem. It's designed specifically for building stateful multi-agent systems, its core principle. Model agent workflows not as linear chains, but as graphs. Think of it as providing the blueprint and the connective tissue for truly autonomous, collaborative AI teams.
Okay, a graph. Sounds a bit technical, but powerful. Can you break down the core components? What are the primitives when you think in terms of a graph model? Maybe use that factory analogy again.
Certainly. In the LangGraph, you mainly deal with three things: nodes, edges, and state. Nodes are like individual specialized workshops or processing stations in your AI factory. They do the actual work. A node could be an LLM call, running an external tool, some data processing. Each node gets the current state of the project, does its job, and then maybe modifies the project state or does something external like send an email designed to do one thing well.
And edges are the pathways. Explain the workshops.
Yes. Edges define the path or flow of execution from one node to the next. They're the conveyor belts or traffic controllers. Edges can be static connections straight from A to B for linear flow. Crucially, they can also form cyclical paths, allowing loops like sending a project back for refinement. And maybe most powerfully, they enable dynamic branching through conditional edges. These are key for agentic systems. They route execution based on conditions within the current state. Like, an edge might send the workflow down path X if a query is complex, path Y if it's simple, or maybe route to a human if something looks weird.
So the workflow adapts based on what's happening. And the third piece, state. That's the game changer you mentioned.
Absolutely. State is the heart of LangGraph. It's a shared data structure or memory maintained across all nodes. It's the central project file everyone accesses and updates. It remembers everything that's happened, keeps the context alive, the current snapshot. LangGraph manages this state automatically. It's typically structured clearly, like a well-organized database for the AI. So everyone knows where to find and store info. It can hold conversation messages, intermediate results, variables, decision history, everything. And LangGraph handles updates consistently, even if multiple nodes touch the same data.
So that shared persistent state sounds like it unlocks a lot of the dynamic capabilities of agentic AI we discussed earlier. What unique things does this graph structure enable that a traditional linear approach can't easily do?
Because of the graph structure and explicit state, LangGraph offers several powerful capabilities. First, looping and branching. Agents make truly dynamic decisions. Go back to a previous step loop or choose different paths based on the state branch. Highly adaptive problem solving. Second, inherent state persistence. The AI maintains context over long interactions, remembers prior info, even across sessions, thanks to built-in checkpointing. Third, built-in human-in-the-loop, HITL, functionality. Critical for safety and quality. You can literally pause the AI for human input or review, then resume. And finally, for developers, there's time travel. Amazing for debugging. You can rewind the workflow to previous states, see the execution flow, understand exactly what happened, like rewinding a video of the AI's thought process.
Time travel for debugging. That sounds incredibly useful, especially with complex agent interactions. But why does LangGraph excel over, say, traditional programming loops and if statements? Those also allow iteration and conditions.
Right. While traditional loops and conditionals are fundamental, they're often linear and lack the flexibility needed for the complex, stateful workflows of agentic AI. LangGraph offers key advantages. It has explicit state management. Workflows actively maintain and modify context across nodes in a structured, transparent way. Then, those conditional transitions enable runtime decisions and dynamic branching in a clear, graph-defined way. Much more intuitive than deeply nested if-else logic for complex flows. For developers, modularity is huge. Each node is independent, reusable. Plus, enhanced observability. Clear insights into the execution path, vital for debugging complex systems. And finally, a clear separation of concerns. Routing nodes, flow control, are separate from processing nodes, state modification. Improves clarity, maintainability.
So it's specifically designed for those sophisticated AI agents that need to make complex decisions and adapt on the fly. Can you give us another example? How would LangGraph handle a real-world scenario better than a traditional approach?
Sure. Think about that complex customer support agent for a big online retailer again. A traditional while loop might let it keep asking for input if the query is unclear. But it wouldn't easily remember past topics, seamlessly branch off to a totally different support flow for a specific issue, or pause for a human supervisor only for sensitive cases. A LangGraph workflow, though. It could dynamically branch for different issues, refund versus tech bug. It could loop to retry input if needed. Crucially, it could pause for human input at a critical point, say, before a big refund, then resume autonomously after approval. All while retaining full conversational memory and context from the start, even across pauses. This dynamic adaptability, persistent memory, human oversight, that's what makes LangGraph powerful for production-grade agents.
That makes it crystal clear. Okay, let's nail the direct comparison. If someone's looking to build an LLM app, when should they reach for LangChain? And when is LangGraph the better tool?
Yeah, it really boils down to the complexity, interactivity, and dynamic nature of your workflow. LangChain's primary focus is general-purpose LLM app building, chaining operations together. Its structure is a chain, a directed acyclic graph, DAG. Tasks move forward, no loops allowed. Its components are things like memory, prompt, LLM, agents forming chains, document loaders. Its state management is more limited, passing in go forward. It has memory components, but not that core shared global state. LangChain excels at sequential tasks, retrieve, process output. LangGraph's primary focus is specifically creating and managing multi-agent systems and stateful, non-linear workflows. Its structure is a true graph, allowing loops and revisiting previous states, ideal for interactive systems, evolving conditions needing dynamic replanning. Its fundamental components are nodes, edges, and state. State management is far more robust, a core, shared component accessible and modifiable by all nodes, enabling complex, context-aware behaviors over many turns. Use cases. LangGraph is ideal for complex systems needing ongoing interaction and adaptation. Virtual assistants with long memory, multi-agent collaboration on intricate projects.
So it sounds like LangGraph is almost a more specialized, heavy-duty version for specific complex use cases, but it builds on the LangChain foundation.
That's precisely it. LangGraph is a specialized library within the LangChain ecosystem. It builds upon LangChain's components, taking agents and chains to a more advanced orchestration level. Think of LangChain as the comprehensive toolkit for all your LLM building. LangGraph is the specialized, high-performance engine for the really complex, stateful, multi-agent stuff, built using those LangChain tools.
That's a crucial distinction for our listeners. So practical guidance time. When should you use LangChain versus LangGraph for your next AI project?
Okay, you should use LangChain when your workflow is clearly defined and linear, steps always follow a predictable sequence, or when you need to build quickly, prototype MVPs. It's also great if you need broad integrations for lots of different models, tools, data sources. Excellent for chaining together known sequences without needing dynamic, iterative behavior.
And LangGraph, what's the trigger for choosing that?
You should use LangGraph when your application demands complex, non-linear workflows, with branching paths, loops allowing revisits, conditional steps adapting to the situation. It's the go-to for stateful interactions where context needs to be robustly maintained across many turns or actions, or when building multi-agent systems where multiple AIs need to coordinate, share info, adapt together. Plus, if you need fine-grained control for production-grade reliability, traceability, and durability, LangGraph's explicit structure helps. Basically, if your system needs to make dynamic decisions, remember lots of history, learn over time, or involve an AI team, LangGraph is your choice. It's for when your AI isn't just generating, but truly managing and adapting.
That provides a very clear roadmap. Okay, let's dig a bit deeper now into the architectural principles and practicalities of actually using LangGraph. This isn't just coding, it's designing smart, robust AI systems for the real world.
Indeed. The power of graph architecture in LangGraph isn't just theory. Its purpose is to explicitly tackle the limits of traditional linear programming in dynamic AI workflows. The advantages are clear. True dynamic decision-making, branching, and looping based on runtime conditions for adaptive behavior. Clear visualization diagrams showing nodes and edges make understanding and debugging complex flows way easier than tracing sequential code. And it promotes reusable components, modular nodes doing specific tasks, tested independently, like interchangeable parts.
So back to our complex support agent example, this graph architecture is exactly what lets it handle different issue types via branching, retry inputs with loops, pause for humans, all while keeping full context. A linear system just couldn't manage that effectively. It's the difference between a rigid path and a flexible network.
Exactly. The graph provides the framework for that sophisticated behavior. Now let's talk state design best practices. The state is the memory bank. Its design is crucial. Key principles. Clear naming for state variables. Use descriptive names like user query, agent response, issue type, retry count. Makes it immediately understandable. Also, aim for flat structures. Avoid deep nesting. Makes manipulation and reading easier, like clearly labeled folders versus files buried deep down. Ensures the AI always knows where its info is.
So you define the shared memory structurally, like database fields for the AI's internal thoughts.
Precisely. You could define a support agent state with distinct fields for user input, agent response, issue type, retry count, a clear, consistent blueprint for the workflow's memory, vital as complexity grows.
And the nodes themselves. How should they be designed for best results and maintainability?
The core principle for node design is single responsibility. Each node does one clear task. This modularity simplifies debugging, makes components reusable. Nodes can be categorized. Processing nodes transform data. Validation nodes check conditions. Integration nodes talk to external systems, APIs, databases. Decision nodes direct the workflow based on the state. All communication happens via the state. Nodes read inputs from the current state, do their task, update the state with outputs. Keeps nodes focused, avoids messy direct links.
So the state is the central nervous system, keeping information flow clean. And how do the edges, the traffic controllers, manage the flow dynamically, make those on-the-fly decisions?
Right. The role of edges is dictating flow. A common, powerful pattern uses simple conditional logic. You define a special function, it takes the current state, looks at conditions within it, and returns the name of the next node to execute. For example, a routing function checks retry count or issue type in the state. It dynamically decides, go to human review, interaction, issue resolved, or continue processing with another AI step. Highly flexible, adaptive pathways responding to the situation.
That makes the workflow truly dynamic, like how a human adapts in conversation. But what about errors? Error handling is essential for any robust system, especially an autonomous one.
Oh, absolutely critical for production-grade workflows. You must plan for errors. Key strategies include error-specific state fields like error message or last attempt failed in your state schema, so the AI knows something went wrong. Create dedicated error handling nodes for processing or logging errors, maybe notify a human, trigger an alert. And importantly, implement graceful fallbacks to alternative paths when things go sideways. Common patterns. Retry nodes automatically try a failed action again, maybe with a delay, limited attempts. If retries fail, error nodes route to human intervention, logging systems, notifications. Ensures failures are caught and handled without crashing everything.
So it's about building resilience right into the graph, making it sort of self-healing. And for developers, testing, debugging, performance, how do you manage that with these complex systems?
For testing, best practices include node isolation test each node function independently. Ensure predictable states, same input state, gives same output state for reliable testing. And incremental development, build and verify step by step, add complexity gradually. For debugging, LangGraph's time travel is invaluable. Rewind to previous states, see the execution flow, state changes at each step, pinpoint issues precisely. For performance, keep the shared state lean, minimize state complexity. Only store what's necessary. Isolate costly computations, complex LLM calls, big database queries, in dedicated nodes for focused optimization. And use caching for repeated, expensive operations to avoid redundant work, speeding things up.
And integrating with the outside world, bringing humans in effectively. These systems don't live in a bubble.
For connecting external systems, isolate integration logic in dedicated nodes. Always anticipate failures, timeouts. Robust fallbacks, external APIs can be flaky. When incorporating humans effectively, design clear points where workflows can pause for human approvals or reviews. Provide straightforward ways for human decisions to feed back into the workflow. Let them guide the AI at critical points or take over when needed. Ensure safety, quality control.
Finally, any common mistakes to avoid with LangGraph, and how does the framework help steer clear of them?
Yeah, a common one is oversized nodes doing too many unrelated things. Kills modularity, makes debugging hard. Another is deeply nested or unclear states. Makes the schema hard to manage messy memory for the AI. And a critical one, ignoring error conditions. Not planning for failures leads to brittle systems that break easily. Instead, follow the best practices. Modular nodes, single responsibility. Explicit state schemas, plan for errors early. LangGraph's structured approach naturally guides you towards this, making it harder to fall into those traps by design.
We've covered a lot on LangGraph's architecture and principles. Now let's bring it all together. How would you actually get started building a basic application? Seeing the steps really helps crystallize how these pieces work together.
Yes, the practical steps make the theory concrete. Let's recap the key components you'll use. You define your state, that evolving memory-holding workflow data. You create nodes functions, processing the current state, modifying it, or causing side effects. And you have edges defining flow between nodes, passing the updated state automatically.
And within edges, the two main types, straight connections and the dynamic ones, right?
Exactly. Direct edges are simple. Node A finishes, updated state goes straight to node B, like a linear conveyor belt. Then the powerful conditional edges. They let the workflow make dynamic choices. They take a function that looks at the current state, decides which path to take next based on conditions in that state. The function returns the name of the next node, allowing flexible routing.
Got it. So what are the general steps to building a LangGraph app? The sequence a developer follows.
Okay, first, you create the core graph object, initializing it with your defined state class. Second, you incorporate your nodes, adding your processing functions to the graph, giving each a unique name. Third, you connect nodes with edges, defining the flow simple linear connections or complex conditional logic. Fourth, you set the entry point, telling it which node starts the workflow. And finally, you compile the graph. This builds the runnable application ready to go.
Okay, so once it's compiled, how do you run it? Can you walk us through a simple example, maybe using a counter to show that loop behavior? That's always the aha moment for me, seeing the persistent state update through a cycle.
Let's do a simple counter loop. You start the compiled app by giving it an initial state. Let's say start with counter at 1 and an empty letter placeholder, app.invoke. Here's how it flows. The initial state, counter 1 letter, goes to a node, let's call it increment generate. This node bumps the counter to 2, maybe generates a letter, say A. The updated state, counter 2 letter A, automatically passes to a display output node. Display output just prints the current counter 2 and letter A. Crucially, the updated state then hits a stop condition, which is a conditional edge. Inside stop condition, it checks if counter 13. Since counter is 2, this is true, the condition signals continue. The conditional edge based on continue dynamically routes the workflow back to the increment and generate node, and the cycle repeats. Increment and iterate updates, counter and letter, AG counter 3, letter B. Display output shows it, stop condition checks again. The shared state keeps updating, remembering the latest values. This continues until the counter hits 13. When counter 13, the stop condition signals end. The conditional edge then transitions the workflow to completion. It stops.
That's the loop. And when it's done, the invoke call returns the final state, right? Which would show the counter at 13. That's incredibly clear. Shows how the shared state keeps context alive through iterations.
Exactly. The final state snapshot gives you the outcome of the whole dynamic process, a clean way to get the result.
And finally, visualization. You mentioned that. Seems key for these complex graph structures. One thing to understand concepts, another to see them.
Absolutely. When dealing with complex workflows, many nodes, dynamic edges visualizing is vital. For understanding, debugging, explaining to others, LangGraph workflows can be clearly represented using common diagramming tools, like mermaid diagrams. They intuitively show nodes and edges, making the structure much easier to grasp and troubleshoot. Helps you build intricate systems with clear, maintainable structures even as they grow, like having a constantly updated blueprint of your AI's brain.
Well, we've covered a lot of ground. We journeyed from understanding the basic differences between reactive generative AI and proactive agentic AI. Seeing how multiple agents can form sophisticated teams tackling complex, multi-step goals. Then, we explored LangChain as that foundational builder for LLM apps, and finally, took a really deep dive into LangGraph, the powerful framework enabling these stateful, dynamic, collaborative AI systems through its unique graph architecture, allowing loops, branches, continuous learning.
It's been quite the journey, yeah. We've seen how LLMs shift from being just content generators to becoming the core reasoning engines of increasingly autonomous agents, and how frameworks like LangGraph provide the architectural blueprint for these intelligent systems to coordinate, adapt, and remember.
And for you, our listener, understanding these distinctions, it isn't just academic, is it? It's really key to navigating the future of AI, from the chatbots, to intelligent collaborators managing complex processes in work and life. The way we interact with and build AI is fundamentally changing. These tools, these concepts, they're at the cutting edge of a shift that's going to impact, well, almost everything.
Indeed. The shift from reactive tools to proactive collaborators changes not just how we build AI, but how we might work with AI, how we even define efficiency and autonomy in a digital world.
Which leaves us with a final provocative thought to chew on. As AI becomes more agentic, less a tool we command and more a collaborator we work alongside, what new questions about oversight, about ethics, will we as humans need to proactively address? How do we ensure these powerful systems always align with our best interests?
A question that truly demands our attention as these capabilities race ahead, and one we need to keep exploring as AI takes on more and more responsibility.
Until next time, keep digging deeper.